Good evening and welcome to all in our next video lecture on classical mechanics. Topic: potential energy in Lagrangian mechanics. So far, especially in lecture 7 and 8, we have seen expression for kinetic energy capital T in different coordinate system. Now we would like to define another important thing, potential energy. But before starting the video, we from the team of Step Up Bengal request all of you to just share, like, and comment on our work so that we can improve each time for the benefit of the students from math background who are preparing for net oblique set exams. So without any delay, let us start the main topic, that means potential energy. Potential energy, in fact, as we have already discussed in our previous lectures, energy is always determined by amount of work done. So potential energy is one type of work done. How does it happen? If we recall a very famous equation of motion that is called EOM, that is simple harmonic motion, then we all know that its equation of motion is x double dot equal to minus of k into x. Just if we multiply this quantity kx by mass m here and here also, then we see that this is mf, that means total force F. So here is also the total force F multiplied by, where this quantity is multiplied by m. So force per unit mass, force for m mass, we have minus mkx. Force for unit mass, we have only minus kx. This is denoted as, in general, capital F. So here the result is mf equal to force. This minus kx is mx double dot equal to force F into m. F into m. For unit mass, this becomes F. Potential energy V is denoted by V, that is potential energy. Say we can take one stone from ground level, that is zero level, when Z is 0, because in general we would like to uh, describe vertical system by Z. Vertical system কে আমরা Z হিসেবেই ভাববো। সেক্ষেত্রে আমরা, if we take this up to height Z and put it here on a particular platform, then obviously if we do this experiment in gravitational field, then we cannot ignore mg, that means the force downward gravitational force. So against the force we are traveling along positive z axis. This is extremely critical. That means positive z axis means z axis here is measured vertically upward. Then this mg is working in the opposite sense, and we have taken this stone, say, of mass m to this height. Say this height is our z. So what will be the work done? That will be the potential energy which will be stored in this particular stone. এই স্টোনের মধ্যে ওইটা পোটেনশিয়াল এনার্জি আকারে স্টোর হবে। তাহলে সেটা কি হবে? বলছে ফর্মুলাটা ভেরি ইজি ফর্মুলা, ভি ইকুয়াল টু মাইনাস অফ ইন্টিগ্রাল ওভার এফ ডট ডিএক্স. So here, as we have done this experiment in the direction of z axis, so we can just replace it as f dot dz, and also this f, one second, also this f will be replaced by minus mg, because this is the total force. If we call it, if we can take F both as force per unit mass, we can call it force per unit mass, or sometimes as total force. When we call it force per unit mass, then remember we have to divide it by m, mass, and when it is total force, then there is no need. Here we have taken it as total force, so ultimately this becomes mgz plus c1. Now say one thing, take a look at one thing. When z is 0, that means no displacement is there, obviously no work done, and potential energy and all type of energy are ultimately work done. So we can say V equal to 0 at z equal to 0, where at ground level. At ground level this is obvious, so C1 is obviously 0, and ultimately we get V equal to mgz. Remember that very important point for any exam point of view, that z axis, this terminology is used in question paper. Z axis is measured vertically upward. If z axis is measured vertically downward, then this sign minus mg will not be required, because we are doing work not against mg but in favor of mg. So ultimately this minus sign eliminated, and v becomes in downward case minus mgz. These two are extremely important. We would just like to replace this z further by mg into that z is vertical displacement. Why we are making this change? Because it may so happen that this vertical direction is denoted by x. In that case, this expression will become mgx, and this will become mgx minus, or it may look like mgy or minus mgy. So it is important that what notation we are imposing on it. If it is vertically upward, then we will always take positive sign, and it is vertically downward, then we will take negative sign. These 2 points are extremely important for exam point of view. So ultimately we have done potential energy in case of vertical displacement. Now comes again one of the most beautiful thing, that is in case of SHM, simple harmonic motion. One type of such motion example is given by elastic, the motion of elastic string. String মানে সামান্য পেঁচানো তার, just coiling like this, and a mass is attached, and if we just take it say up to distance x and then remove it, say its original length is L, then this is performing SHM. That means the motion will be about a particular point, once to the right, once to the left, and its equation motion is very famous, that is x double dot equal to minus of kx, where the important point is k should be greater than 0, because if k is less than 0, then this will become positive. Actually, why do we take negative sign here? This is important, because if the particle say p is here, that means particle of mass m is here, then in case of SHM it is always enjoying an against force that is towards a fixed point, say O here. So since the force is always towards fixed point O, it is taken to be negative. So this is the actually force per unit mass. Now if we want to derive potential energy, then what will be the expression? Simple case, negative sign over f dot dx. Now equal to minus of what is F? Here F is taken to be force per unit mass, so that will be minus kx dx. So ultimately this will become half kx square plus c1, where c1 is integration constant. Again see that if x is 0, no work done is possible, that means potential energy is 0. So ultimately V equal to half into K. The beautiful thing is that the point to look, this X is elongation. It may be contraction also, মানে এটা ভিতরের দিকেও যেতে পারতো, এই দিকে হতো তখন চলে যেত ভিতরে। সো এইখানে হেয়ার উই উইল অলওয়েজ ইউজ elongation oblique contraction whole square. So this is called spring mass system. This is important. This is called spring mass system. So whenever we see spring mass system, its potential energy will always be half kx square type. This result you should remember very well, because if we ask students, they often call it potential energy as mgh, or say mgz, or say mgx, such type. So the only one idea they usually like to have is, whenever we call about potential energy, mg should be there always, but it is not true. Mg will come only if all the work has been done in the field of gravitational field, or rather by the effect of gravitational force. But in general, any force F can be used, and in spring mass system we have seen this particular most beautiful result. Just you should mark it with red color. This is very important. We will see in a minute why it is important. Half k x square. Clear? Now we can easily solve all the problems if we just recall this particular result, and how to calculate potential energy, how it becomes mgx, or like, or rather minus mgx in case of vertical displacement under gravity, or in case of general force. Now comes the question that when we have defined T kinetic energy and V also, and take a difference of those two by assigning T first then V, this is called L. This is called a function which is called Lagrangian function. Now say, take a look at one thing. If all the thing is happening in one dimension, then this becomes half into mx dot square minus V becomes spring mass system half kx square. So this is of the type, this can be, L can be written as a function of x comma x dot, and obviously time. Some call it L x comma x dot. So whenever we talk about Lagrangian, we have to recall the idea of generalized coordinate, which we have discussed in our previous lectures. Those who are new to this particular lecture, please revisit, otherwise you cannot have good idea in exam hall. First of all of you should try to get good idea about a particular subject, then you can only solve it, any problem, within 2 to 3 minutes. Now L, what is L? If we call generalized coordinate, then coordinate x was in general written as qi, comma, here we call x dot, that was velocity, so qi dot of comma t, and someone like to write it as qi comma qi dot comma t. So Lagrangian function L is always written as a function of displacement, velocity and time. And often this time is not written because it is imposed automatically, as there is q dot. This dot is taken with respect to time. So in some book we see this version also. Clear? This Lagrangian formulation is very much important for exam perspective. In various coordinates, they ask question about it. Now, in this particular video, before finishing, we would like to see one of such question which came in CSIR. This question is chosen CSIR net math, obviously for math background students, June 2017. We don't say that we can solve it in 30 seconds, because that will be a demand that is, I think, is improbable. That is not possible always, but we can solve it in 2 to 3 minutes. But if we go just classical way as in MSc syllabus, then it may take say 10 minutes or 15 minutes. Then it becomes difficult to qualify those exams. We have to solve it within 2 to 3 minutes. Now take a look at the problem and use all the concepts in especially lecture 7, 8 and 9. We would like to solve this by using all these lectures. Please revisit all these lectures for theory. সব থিওরিগুলো এখান থেকে ভালো করে দেখে নাও, সবাই ইজিলি এটা করে ফেলতে পারবে। এটা নিয়ে আতঙ্ক, জাস্ট ডোন্ট বি প্যানিক in case of any classical mechanics problem. In any case, just comment, drop a comment in the comment box, and we would like to satisfy all of you. Consider a spherical pendulum consisting of a particle of mass m. Now the point comes, what is spherical pendulum? In simple pendulum, the motion is like as we have already discussed, from right to left, from left to right. But when it becomes just it goes to here, if additionally it is rotating, say there is an axis about its center and it is rotating about this, then one motion is this in this direction and also the rotation is possible. That is called spherical pendulum. Just you have to know this particular concept. Otherwise here it is not of so much importance, because the only important thing is to like and is to realize which coordinate system we would impose on to solve the problem. That is the main question, which coordinate system. If we quickly realize what is the most suitable coordinate system, if it is mentioned, it is well. If it is not mentioned, then if we just can realize which coordinate system is to be used, then it will be easier. Moves under gravity on a smooth sphere of radius a in terms of spherical polar angle theta and phi. And we all know that in spherical polar coordinate system, we have discussed in lecture number 8, kinetic energy T, that is given by half into m into r dot square plus r square theta dot square plus finally we have replaced r by r sine theta, so r square sine square theta into phi dot square. This was the expression for kinetic energy. So here they have given that it is happening about it is happening with respect to a fixed radius a. So here r equal to a, we have discussed it in the theory, please revisit those. R dot equal to 0, so kinetic energy will become half into m into here this r will look like a square into theta dot square plus this finally will look like a square sine square theta into phi dot square. So kinetic energy becomes up to this. Then comes the point, can we take this a square also common? Yes, half into m a square into theta dot square plus sine square theta into phi dot square. Now take a look at the beauty. Next we have to just find v, because they have asked about Lagrangian. These are keywords. Lagrangian means L. So L is what? L is T minus v always. So T is done by using lecture 7 and 8 and V is done by using lecture 9, because downward vertical direction is mentioned. Take a look at the beauty. We have already discussed, when there is upward positive sign, downward negative sign, and what will be that? mgz. So here we see what is that. Here V will be minus mgz. but we have discussed in lecture 8. Just revisit that here, that z in spherical polar coordinate system, the relation between z and Cartesian coordinate system xyz is z equal to r cos theta. Just revisit lecture 8. Here we will see this expression. Then mgz, then what does it becomes? Then it becomes mgz means r cos theta, but r is given to be a, so minus mga cos theta. When you will be writing it in exam hall, then don't no need to just put r here, just put it here. But for first day we would like to go in detail so that we can ultimately solve it within 2 to 3 minutes. Now all the expressions are in our hand and we can easily solve. So what will be L? L equal to T minus B. What is T? In the previous page, half into M into A square into theta dot square plus sine square theta into phi dot square minus. Now take a look at the beauty. For downward vertical, already one minus sign is there. So our sign will be ultimately this minus plus again this second minus, that means mga cos theta. Ultimately this will become half m a square theta dot square plus sine square theta into phi dot square plus mga cos theta. Clear? I think all of you have good idea about this up to this particular point. Next we should just take the expression, all the answers. In all the answers, ma portion is common. So if we just take m common, just take a one thing. Here the sign is plus in front of mga cos theta. So in the options where negative sign is in the second portion, that means in potential energy portion, these two options will clearly be eliminated. Now the question comes whether it will be g cos theta or g sin theta. Is there any need to calculate these two portions? Is there any need? We will say no, because we have already seen that here is mga cos theta. So the sin theta option is also eliminated. So the answer will be clearly option 2. I think all of you have good idea about it. So can we demand that we can do it in 30 seconds? It is unrealistic. We can do it, yes, within 2 to 3 minutes. Just take a look at the kinetic energy and potential energy in lecture 8 and 9 and you will just easily solve the problem. That was set in CSIR June 2017. This was 3-mark question. So 3 mark for 3-mark question, we cannot afford to give more than 2 to 3 minutes, because that if we just apply here 10-minute technique classically as in MSc syllabus, then to qualify the exam will be difficult. Clear? So I hope all of you have good idea about it. In the next few lectures, we will discuss about all the problems of competitive exam on Lagrangian system, on rather Lagrangian, that means T minus B formation from now on will be important. So up to then, goodbye.